proceed in a linear fashion. When they go
This
down
way
linear-
or this way? As far as linear fashion goes, this way or that way?
There's many lines. Many lines.
Many lines?
I'll have to do the vector sometime. Figure it out.
Is it piecewise defined? It goes up for a while and then down.
Yeah, sure.
And
It's piecewise defined, but I set the intervals in a random number generator. And the bounds are really large, so sometimes they're really long periods of one way or the other.
then, gotcha. I feel that. Sometimes I switch really quickly. I get it. Oh, homework?
Yeah.
How'd the homework go?
I don't know how to read.
Not too bad, actually.
Well, good. Very normal.
Why would you read? I don't know. I don't know what I thought I should.
What questions do you have?
Can I ask questions about the review?
Of course.
Okay. I have a few.
Okay.
So on number 14, parts E and F, it says to find a unit of, and then it's like the integral.
Yeah.
Z,
Yeah.
and it says like 2 cubed times 7 to the 5th times 11 squared. That is not 1. I don't really know what.
Is that what it says?
Yeah.
Okay, cool. All right. So, what does it mean to be a unit?
It has a multiplicative inverse.
Good. It has a multiplicative inverse, right? So I need to find something that has a multiplicative inverse with that particular, or in that particular ring, right? So when we've done multiplicative inverses before, pardon me, we think about trying to solve the AX equals 1 equation, right? Right. So how did we go about figuring out an inverse for this thing, modulo n? What did we do? Or what needed to happen, I guess I should say. Not everybody at once. Okay, let's go back and ask some other questions. What do we know about everything in any Zn? It's either a unit or a... Yeah, it's either a unit or a zero divisor, right? It's the only two choices you have. That's actually true in any finite ring. It either has to be a unit or it has to be a zero divisor, one or the other. Okay? There are no elements like you get in Z where it's neither a unit nor a zero divisor. Okay? Only units and zero divisors. If we had something like, let's do something smaller. Let's say I had Z15. Tell me something in Z15 that is definitely a zero divisor. Why?
Divides 15.
Okay, it divides 15, right? I can 3 times something will give me 15 or a multiple of 15, right? So 3 times 5 gives me 0, right? So that would be a zero divisor in there. Can you tell me a unit in Z15? 2 works. Why does 2 work?
Does not.
It doesn't, yeah, and even better, it's relatively prime to 15, right? The GCD of 2 and 15 is 1. Remember when we have the GCD as 1, if the GCD of A and N is 1, then we can always write that as a linear combination this way. And then if we're doing mod N, that piece goes away. And so you get that solution. The X is what you need for your unit. Okay. So going back over to this, how do you think you're going to pick a unit out?
All 3 of the factors.
Okay.
And
N, sure, I'll say N. Yeah, notice there's only 3 distinct prime factors of that number, right? 2, 7, and 11. If I want a unit, I want to make sure that I have a GCD of 1 so that I can always do that linear combination idea. So that when I mod out by the end, that second part goes away, and I get my multiplicative inverse. So tell me something that's relatively prime to that big number. 3 works, right? There's not 3 is a prime that's not in that prime factorization. So that's how. So I could do 3. I could do 5. I could do 8. Not 8. 9. Can't do 8. 8's in there. 2 cubed is 8. I could do 9. I could do. Can't do 10 because it's not relatively prime to the 2. I could do 13. Not 14. You could do 15 again. So you got lots of choices. But that's how you do that one. I'm just looking for something that's relatively prime. Basically, that was just a matter of do you know what the words mean and do you know how to find units of the Z mod ends. So if I asked for a 0 divisor in that ring instead, what would you tell me? That's not 0. I like a cup.
Thanks.
2,
Yeah.
7, 11.
Yeah, those all work, right? Because remember, to be a 0 divisor, I just need to find something that's not 0 to multiply by it and get 0, right? So if I claim that 2 is a 0 divisor in that ring, what would you need to multiply 2 by to get 0?
2 squared times 7 to the 5th times 11 to the 2nd.
Yeah, just the rest of that particular number, right? And that's certainly an element, a non-zero element in Z mod that thing, because it's smaller. So if I ask you a question like that, I'm asking you to find basically something that's relatively prime and not relatively prime. Yeah. Does that make sense?
Yeah.
Okay. So again, the whole point of that question is, do you know what the words mean for unit and 0 divisor? And then do you know the properties of Zn and what makes it a unit or a 0 divisor? That's mainly a way to ask a definition question without you spouting a definition. Isn't that fun?
A bit.
That's, those types of questions are part of the number theory origin of the topic too. Yes.
Just a clarification. To prove identity, you just need to prove a unit exists.
To prove a multiplicative identity,
Yes.
you need to find something that works as a multiplicative identity. So you wouldn't know that you had a unit unless you had the identity to start with.
Okay.
Because I need to be able to write AX equals 1, and I need to know that the 1 exists to start with.
In Calc 3 today, Olson was using unit and identity interchangeably, and I was sitting there panicked, like, oh my god, did I do my homework wrong?
Identity for a vector? Or
Yes.
because we talk about unit vectors?
Yes.
Okay. Gotcha.
And then she did a sidebar and was like, "Good for those of you in abstract if you talked about identity." I'm on the spot here.
It'll be just you. Yeah. Yeah. So what's that?
That's the I better know something.
Now, the tricky part is that identity and unity are used interchangeably. Those two mean the same thing, but unit means something different.
Okay.
But if you know that a ring has units, it has to have an identity to start with.
Okay.
It may be the case that your only unit is the identity. Simple example is Z2. Because you only have 0 and 1. So there's only one non-zero element in there anyway, and it is the multiplicative identity. But to give a better example of that, if you do Z2 cross Z2, that gives you more elements, but there's only one one unit, it would be the identity. So the identity is always a unit. So you have to start there. So if it has an identity, you're always going to have at least one unit, but you might get more depending on the ring. If you start talking about, we haven't done any groups. This is why I don't like doing it this direction. Most of the time you do groups and then rings, because there's a piece of rings that is a group part all the time. If you have something that has a group part, the additive part isn't just all a bunch of Z2s. You're always going to get at least 2 units if you have an identity, because you get the identity, the multiplicative identity, and its additive inverse are always units. So to get only exactly 1 unit is a very special type of structure for the group part. So usually you get at least 2. So for example, the integers has 2 units, 1 and -1. Z6 is another one, has 1 and -1 is 2 units. The -1 just happens to be 5. But unless your group part, unless the additive part is just a bunch of additions that you're doing modulo 2, you're going to get at least 2 units if you have an identity. Anyway, that was a long excursion into some more advanced thoughts. Yeah, it's okay. Thinking about things is a good thing. It's what you're supposed to do. Think about things, ask questions, make messes on papers. I was working on your test today. Messes all over my office looking at different things. Playing around with elements. No, it's not. It's not a bad thing. I'm just trying to get it to work. I was trying to get it to work nicely. So that's not a bad thing. It shouldn't be an unexpected thing either. So anyway, other questions? Do you have more questions than anything?
I do.
I kind of figured. You typically do. So if it was only one, I would have been surprised.
I'm confused on how to find the characteristic of the ring.
Oh, sure. Okay, because we just mentioned that right at the end of class last time,
Yeah.
right? Okay. So again, pardon me. Your characteristic, if it equals a number, this means that if I add any element to itself n times, I get 0. What is that?
No, I mean it isn't that much.
You're being annoying?
Just a little bit.
To me or to Devin?
I have no clue what you're talking about.
All right. So characteristic mean, and this is another reason why it's in some respects better to talk about groups first. It's the number of times that you have to add every single element to itself to get back to 0. Okay. Pardon me. Now it turns out that if I add the additive identity, there's not the additive identity, the multiplicative identity to itself n times to get 0, then that n that I use has to be the characteristic. It has to be the characteristic. I also need, I forgot to write down, this should be the smallest such n. Did you have one in particular you were looking at? I'm sorry. Or just was one of the
number 17,
which says
it just gives the multiplication and addition charts, and it says
find the characteristic. Gotcha. Okay, so if we want to do characteristic generally, basically we just need to worry about the multiplicative identity, whatever that's identified as. And the reason for that is that if I know that n times 1 gets me back to 0, then I can do n times x as n times 1x, and then do that, and then I get 0 times x. So if I want to find the characteristic of a ring, even though characteristic is defined as the smallest positive integer that when I add every element to itself that many times I get 0, I really only have to check it for the multiplicative identity, if there's an identity. If no such n exists, then we say the characteristic is 0. So if you've got like the integers, for example, if I add 1 to itself over and over again, all it does is get bigger and bigger. Right? Okay. So let me pull up the problem here if I can get out of this easily. Okay, I don't have problems doing things with this anywhere other room besides this one. I don't know what the problem is. It doesn't like me. Review. Zoom. 17. Scroll. Oh, stupid thing. I love how the default on this is, oh, you want to select a bunch of text in the PDF rather than scroll the damn thing. Anyway. All right. There are the multiplication and addition tables for that. From the multiplication table, can you identify the multiplicative identity? Which one? I think so. Multiplicative identity. Yeah. Okay. It should look the row. If I look across the row, it should look exactly like the top. And if I look down the column, it should look like exactly like the left. So we see that hopefully that the multiplicative identity is E. All right. So if I want to know what the characteristic of the ring is, then I'm going to go over here to my E, and I'm going to add E to itself as many times as I need to get to 0. So E plus E is A. So that's twice so far, right? E plus E is A. So that's 2 times. That's not 0. E plus A is B. So now I've added it 3 times. Still not 0. E plus B is C. That's 4 times. E plus C is D. It's 5 times. And finally, E plus D gives me 0. So it has characteristic 6. So just reading it, basically going through the table. So if you had something like that, and then oops, I missed one. What do I want to do? Like that. So I had that for my addition and multiplication table. That actually doesn't work for a ring, by the way. I filled that out. Okay, looking at that table, the right one is your multiplication table. Hopefully that's pretty clear because I put 0 times those things are 0, right? Okay, so, pardon me. What's the multiplicative identity? A, right? Again, it repeats the row at the top and the column at the left, right? So A is multiplicative identity. What's the characteristic then? 2, because I have to do A plus A. It gives me 0 immediately. So that's what the characteristic would be. The table. So that helps. Okay. What would your characteristic be for any Z mod n? That's that question. What's the multiplicative identity for Z mod n? 1. How many times do you have to add 1 to itself to get to 0 in Z mod n? N, yeah, right? So the characteristic will always be n. Yeah, so for any of those, oops, the characteristic of Z mod n is always n. Let's do something fancy. It's always a danger, isn't it? He wants to do something fancy, it's going to be hard.
Just making sure I understand. So, like, the characteristic is just that one time that the multiplicative identity adds to itself to get 0.
Yeah. Yep. The multiplicative identity adds to itself. That's exactly right. Yep. How many times you have to do that to get 0? Okay, so let's play with a Cartesian product real quick. And we'll do a couple of these and see if we can come up with a general rule. Because this will actually pop up later in the semester, so might as well do it now. You're also happy about it, I can tell. It's fun stuff. It better be fun to me, right? I'm an algebraist, so this better be fun to me. All right. First, I have a Cartesian product. How do you find what has to happen in each factor in order to make sure that you even get a multiplicative identity? What does each piece have to have? A multiplicative identity, right? If you're going to have a multiplicative identity for the whole direct product, you have to have a multiplicative identity for each piece. Okay? All right. What does the multiplicative identity end up being in the direct product, given that you have an identity in each piece? 1, 1. Yeah, 1 for the first one, 1 for the second one, right? So the multiplicative identity here is 1, 1. Now, this is a good thing to talk about because we're doing some review, right? At least I hope this is a review. Hope you're not learning it for the first time. At least this part. Okay. So again, for characteristic, I need to know how many times to add this to itself to get back to the additive identity. What is the additive identity in the direct product? 0, 0. Yeah, it's the additive identity in each piece, right? Okay, so let's just do a few sums and see if we can figure out what's going to happen here. So if I do 1, 1 added to itself, we get what? 2, 2. If I do 1, 1 and add it to 2, 2, what do I end up? Good. And why is it 3, 0? You're exactly right.
Because it's the second half is mod 3.
Good. The second part is mod 3. It's exactly right. The second component is mod 3 when we add. The first component is mod 4 when we add. So what's the next one going to be when I take 1, 1 and add it to 3, 0? What am I going to get? You get 0, 1, right? All right. So let's see if we can be clever about this and see if we can figure it out without having to do the rest of these. I went 1, 2, 3, gave me a 0 in the second component. So if I go 4, 5, 6, I'll get a 0 again. 7, 8, 9, I'll get a 0 again, and so on, right? We agree? Notice it took 1, 2, 3, 4 to get a 0 in the first one. It'll be 5, 6, 7, 8 to get a 0 again. When are they going to match? At 12, right? Right? So if I do, and if I see it this way, if I think about, I mean, I know that the notation in the ring means add 1 to itself 12 times, but we can really think about this going to each component, right? That's 12 times 1 and a 12 times 1. If I'm going to add 1, 1 to itself 12 times, I'm going to add 1 to itself in the first component 12 times, and I'm going to add 1 to itself in the second component 12 times. It really does look like a 12 just distributes, right? We agree? Okay. And we end up with 0, 0. Does anything smaller work? No. Because in order for n times 1 to be 0, n needs to be a multiple of 4 in the first component, and needs to be a multiple of 3 in the second component. right?
LCM stuff.
Ah, that's so good. I love it. So if I ask you for the characteristic of Z6 cross Z4,
Wow.
that's going to be 12. Yeah, it's going to be the least common multiple. Yeah, that's exactly right. Because I need to add 1 to itself a multiple of 6 times to get 0 in the first component, and a multiple of 4 times in the second component. So I need a least common multiple idea to get to the characteristic for the smallest of the two. So in this case will be the LCM of 6 and 4, which is 12. That's fantastic. Now the part of this is going to come up later in the semester is how many elements do these rings have? How many elements are in Z4 cross Z3? We had issues with this the other day, so let's go ahead and remind ourselves. How many elements does Z4 cross Z3 have in it? 12, and the characteristic is 12, right? So it has the same characteristic as the number of elements here, right? In the second one, the LCM is 12. How many elements are in Z6 cross Z4? 24. Notice your characteristic is actually smaller. Okay. What we're going to be going for later in the semester is, notice if I add 1 to itself 12 times, I actually cycle through all 12 elements of the Z4 cross Z3. So I can, basically what that means is I can write every single element of Z4 cross Z3 in terms of one element. That's a special property of a group. Versus I can't do that in the second case. That's where we're headed later in the semester. Okay. Cool. Does that make sense though? So when you've got the Z mod n groups, we've got lots of things that depend on GCD and LCM, right? We said if the GCD was 1 between the number and the n we're modding out by, we got a unit, right? If the GCD was not 1, then it was a 0 divisor. Now we know that the LCM of two numbers is tied to the characteristic of a direct product. So like I said, there's a lot of number theory correlations in these things. Okay. I see you're all super interested in number theory. If you're interested in computing at all, you will do number theory. If you're not interested in computing at all, you may not do that in number theory. When I was at University of Evansville, which is where I worked before I came here 19 years ago, been here a while. We used to have an event where we would invite high school juniors in, kind of as a mission recruiting type of event. Recognize them as being top math students at their schools and feed them. We have a guest speaker. So then we had a guest speaker come in from the NSA, National Security Agency, and talked about basically being a number theorist at the NSA, because the idea of having really, really large primes is important in keeping information secure until, quantum computers are invented and then we're screwed. But the whole idea is that factoring things into primes is hard. That's where most of the coding theory comes from, at least to start with. So one of the professors asked if he knew of any primes that weren't public. Because, like I said, primes are important in security, right? I can neither confirm or deny that we're working on that. So just that it's weird. We know that there are an infinite number of primes, so we know that we can discover them. They're harder than heck to discover. And just because we discover them doesn't necessarily mean that there aren't other ones that we've missed along the way. There's a whole class of them called Mersenne primes. If I remember correctly. So they're primes of this form. We don't even know that there are infinitely many of these or not. I mean, there are some really easy statements that you can conjecture in number theory that are really, really harder to get out to prove. So this is an idea of a Mersenne prime. So you change the n to any positive integer, and then you check if it's prime or not. So for example, if you put in 1 for n, you get 5. If you put in 2 for n, you get 17. Because I have to do 2 to the n and then do 2 to that, right? So if I put in 2 for n, I get 2 to the 4th plus 1. If I put in 3 for n, I get, what, 2 to the 8th plus 1? 2 to the 8th is 128 plus 1 is 129. I did that right?
Let's do
What?
56.
2 dollars 56, so 57. Oh yeah, 2 to the 6th is 64. Sorry, I was late.
Oh, yeah.
So those are what we refer to as Mersenne primes, and those are the ones that are typically searched for. There's actually, if you want to get involved in it, there is the Great Internet Mersenne Prime Search, I believe is what it's called. But anyway, they've networked a whole bunch of different people's computers together, and then they take a little bit of computing power from everybody's computer across the world, and try to search if these things are search for primes. I don't remember if the last one was discovered at Central Missouri or not. It's been a while since one was discovered that I've heard of. Dr. Rolfe usually puts a note on his door when someone gets discovered. A buddy of mine used to work at the University of Central Missouri. They discovered one, and then of course, the number of the digits of these things are just huge, right? They're just ridiculously large. And part of their office suite door, they put a whole bunch of numbers of the prime that they found. Which is pretty cool. That was a long excursion. I don't even know why I started talking about it. How did I get there? Number theory, and talking about computing, and talking about primes, and then talking about, that's where I got to it. Sorry. I'm easily distracted.
Oh, how dare you get distracted?
How did I get distracted by math? I know. What the heck is my problem? All right.
Would number theory be covered in theory of computing?
I don't think they do much in there.
Okay.
But I know that Dr. Olson has done independent studies in it, and so have I. So if you're interested in doing something with number theory, we can certainly talk about it.
I don't know enough about it to say I'm interested, but I will look into it.
Yeah.
It sounds cool. I just
Yeah,
don't know.
it's cool stuff. It's related, like I said, it's related to the stuff we do in here. But there definitely are applications of number 32 coding. Other questions? You have another one?
Yes.
Yes.
Can you explain the difference, if there is one, between an ideal and a subring?
Crap, I didn't delete that out.
No.
I'm sorry. For our purposes, no, there's not.
Okay.
For right now, there is a difference.
Okay.
Subring means it's closed under multiplication from elements within the subring itself. Ideal means that you take an element from the subring and anything else in the ring and do the multiplication that lands back in the subring. That's what ideal is. I meant to delete that out. I just wanted to check subring.
Okay.
The evens, you mentioned that.
I did mention this, yes. So the evens would be an example of an ideal. So I take an even times anything, it's even. So it absorbs multiplication from the ring. That's what an ideal is. So sorry, I meant to delete all those out and change it to subring. I apologize for that. I thought I had done that. My bad. That's on me.
I stared at one of the problems on the homework with the integers would go root 2 in the form a plus b root 2 for a second. Terrified, and then I realized I only had to prove it was a subring and not a ring. And suddenly it was all.
Oh, it's not so bad, yeah.
I just.
Yeah, that would be. I mean, it's not. The proofs aren't bad. It's just long because you have to check 8 axioms, right? So, yeah. Other questions? Yeah.
On the key as well, whenever we had to prove a subring, it only showed if it was closed under addition and multiplication. It didn't have anything about like the identity or the inverse. Do we still have to check those two things too as well, don't we?
For a subring, you just have to show that it's a ring under the same operation. So we started with it had an additive identity and additive inverses and closed under addition and closed under multiplication, right? Well, it turns out that you can simplify that a little bit, and we can simplify it to, this is what typically is called a subring test. We can simplify it to that, let's say S is a subset of R is a subring. I need my S to be non-empty. We don't talk about empty subrings. I know we do empty subsets, but we don't have empty rings. Rings need to have something in them. Is a subring if 1, S is closed under subtraction, and 2, S is closed under multiplication. So you only have to check 2 things. The reason why we only have to check 2 things is that if I know it's not empty and it's closed under subtraction, how do I get the additive identity in there? If I know there's something in S, and I know that if I subtract any element of S from any other element of S, I land back in my set again, how do I know the additive identity is in there? What 2 things do I need to subtract to make sure that the additive identity is back in there? It's just self. Yeah, just take an element and subtract itself, so the 0 gets in there. And then once 0 is in there, how do I make sure all the additive inverses are in there? Well, I take 0 minus the element, and I get the inverse of the element. Okay. So to verify that something is a subring, you really only have to check. Well, you still have to show that it's not empty. You have to show something is in there. And typically, usually the easiest thing to show that it's in there is 0, the additive identity. But once you show it's not empty, you just need to show that it's closed under subtraction and closed under multiplication. And then you're guaranteed the other pieces. And that's what we typically refer to as a subring test. The closed under subtraction part is actually a special case of what we'll have the subgroup test later on. Actually, usually it's called the 1-step subgroup test. We'll talk about that later.
That beats the 7-step.
It does beat a 7-step, but we'll also have a 2-step. And not the Texas 2-step. Okay. Other questions? Is this helpful? I mean, besides my tangent that I went off on.
Yeah. Well, I didn't have the subring test in my notes until just now, so.
Yeah, I think I was going to talk about that today. So I asked about it. I don't want questions that way, so depending on Wayne.
That makes me sound so stupid.
No! That absolutely was not the intent. You're supposed to ask questions. That's the whole point of this exercise. Yes.
So for the subring, we had like theorem 3.2, which had the 4 steps.
Mhm.
Is that like wrong to do, or does it still like work?
Oh, you can do that.
Oh, okay.
Absolutely. It's just longer than you need to do.
Okay.
Yeah.
Just
Yeah.
checking.
This is
Do that on homework.
yeah. No, that's perfectly fine. This is theorem 3.6. You want to not label it? No, 3.2 is perfectly fine. Absolutely. Please use that because we hadn't talked about the 3.6 yet. Yeah. No, it's not wrong at all. I'm sorry for the confusion. I'm good at that though, confusing students.
We just were doing homework earlier than usual, so we can
Awesome.
get stuff done, so we can study more. And this one is
Okay, I gotcha. By the way, I'll get your homework graded by tomorrow too, so that if you want it for the exam, you can have it back. Unless you don't want it back, then I can just shred it if you want. We have a shredder. I'll have Lainey do it as part of the work study.
It'll be my therapy. After I take the exam Thursday.
Just start running things through. I hate this stuff. Other questions?
How long about is the exam?
How long?
Like, how much time should I put aside in my day to make sure that I have enough time for the entire.
I'd probably put 2 hours aside. I don't think it should take you 2 hours, but I would put 2 hours aside just in case you have to, get stuff done, approved or something. You want to make sure you think through it. I don't intend for it to take 2 hours, but I also don't want you to rush through it.
Yeah. But I have 2 hours.
I get that. I mean, if it's something like with class, if you need to take, do an hour before and then go to class do an hour after, I'm okay with that too. I don't have a problem with that.
Do you have a class rep for this?
On Thursday?
Yeah.
No.
Okay.
Yeah.
I think it started at like 10.
Yeah, that's fine. I can be here at 10. That's not an issue. Not even a slight issue.
Okay, cool. Because I don't have hours.
Yeah. Other questions? No?
That was it.
That was
That
it?
was all.
Did you do the whole thing already?
I have the last 2 questions.
Okay, cool.
Oh, I think there was a typo.
Oh no. I never make typos.
The key is right. The key is written right for number 4, but the actual question sheet, it says like then.
Oh, yep. I had to flip it. Yep. It was typed wrong originally, and I flipped it. Yeah, that should be AC divides BD. Number 4. It should be AC divides BD. The B and the C are flipped. And you're right, I did fix it in the key. I was fixing it in the key and just forgot to fix it on the sheet. Thank you. The first parts of those should feel very discrete-y in your proofs, right? Discrete-y.
Oh, this is
Sure.
Are the proofs on the exam going to be like very similar to these?
Yeah, I would think so. Yeah, so using things like, for example, we've done things like you can write any even integer as 2k or any odd integer as 2k plus 1. That uses the division algorithm. So if you needed to break something into cases, you write it as 2k and 2k plus 1, right? Or 3k plus 1, 3k plus 2, those kinds of things. GCD is a linear combination. We've done that, right? Make sure I don't miss things. Yeah, I mean, being familiar with what we mean with the definitions. So being able to write divides as a product, being able to write congruent mod a number as a division statement. Those kind of things. I already mentioned the GCD as a linear combination. Primes, of course. I already said that about mod, being able to prove those properties using division. Modular arithmetic stuff, making sure that you can do those operations. And then we talked about that in the Z mod ends in particular, everything's a unit in the zero divisor. We just mentioned that a little bit ago. When is it a unit? When is it a zero divisor? This kind of thing. For the ring stuff, making sure you can verify things with properties. For example, you had one in your homework and there's one in the review, like that, to fill in the rest of the multiplication table. I'm not going to give you a multiplication table that's 8 elements long. Because if you look at the key, you'll also see there's lots of different products that you have to do to be able to do it. Not commutative. That one's not commutative, correct? Yep. So you actually had to do both directions. Yeah. It would not be.
Just
Yeah. Hey, I had to type all in. I typed it all up. So no, I would not make you do something that long. That's insane. But it also, I mean, if you can fill out, like half of that table, then you know what you're doing. You don't have to do the whole thing. Well, one of the reasons why I want to do the one a non-commutative one is that I wanted to make sure you're thinking about multiplications on the left and on the right for the distributions. What else? Making sure you know what the definition of an integral domain is and what a field is. Those popped up. So in particular, remember, integral domain is no non-zero zero divisors, but also it has to have an identity. Okay, so it's not an integral domain if it doesn't have an identity. And again, when we say has an identity, we mean multiple. Anytime you say something that says has an identity, it means has a multiplicative identity, because all rings have to have an additive identity. Okay, so when we say have an identity, we're talking about the multiplication, not the addition. Okay. So integral domain in particular has to have an identity, has to be commutative, has to have no non-zero zero divisors. Okay. So there's three things that have to be true for an integral domain. Okay. Now, just because something doesn't look like a multiplicative identity doesn't mean it doesn't have one. Let me give you an example of what I mean by that. So let's say I look at that subset. So I look at just what looks like the evens that are contained in Z6. You should be able to tell me why that's a subring to start with. Hopefully it's pretty clear that if I add any of those two things together, I'm going to get one of those things again, right? Because they're all evens. If I add even to even, I still get even. When I do Moraine mod 6, I get an even number, right? So you should be able to explain why that works. Okay. If you look at the multiplication table for this, what's the multiplicative identity in there? Oh, I did the backwards. Holy crap. Sorry. Try that again. Sorry. That's the multiplication table. What's the multiplicative inverse? Or not multiplicative inverse, multiplicative identity. Good Lord. Well, you got three choices. Which one is it? Definitely not. 0, right? So it's either 2 or it's 4 if it has one, right? It's 4. Why is it 4? Yeah, remember again, what I'm looking for is the matching piece, right? 4 times 0 is 0, 4 times 2 is 2, 4 times 4 is 4, right? I get the same thing back when I started with my multiply. So 4 is the multiplicative identity in this case. 4 is definitely not 1, and it's not 1 in the original subring either, is it? Or in the original ring. Why can I not talk right? So notice that this is weird, right? It's a little bit weird. A subring can have a multiplicative identity of a ring that has a multiplicative identity, but they don't have to be the same identity. Okay? The multiplicative identity of Z6 is 1. The multiplicative identity for this subring is 4. Right? It's not the same element at all. Certainly can't be 1. 1's not even in there. So for subrings, your multiplicative identity does not have to be the same multiplicative identity as it was for the original ring. Now, it does work in other ones, right? So if I think of the integers and the rationals, the integers is a subring of the rationals, and they have the same multiplicative identity. They match. right? So it may or may not. It sounds like a good true-false question, right? And yeah, there'll be true-false on your test. But it sounds like a good true-false question. Okay.
So there's some true falses on that test.
Now, on the flip side, this is what makes it more interesting later on for ideals. I told you that we haven't talked about ideals yet. This isn't on the test. But for an ideal, if you want it to be a proper ideal, meaning actually properly smaller than the original, the multiplicative identity cannot be in the ideal. Because again, I told you that ideals absorb multiplication from the ring. If 1 is then there, then it has to absorb every single element of the ring. Because an element times 1 is that element. So if it absorbs multiplication and has 1 in it, it's the whole thing. So it can't be a proper subset anymore. And that'll come up again later when we talk about ideals. Okay. But for a subring, the multiplicative identity may or may not be in the subring. And the subring can still have a multiplicative identity. And like I said, it's weird. Okay. But one of the reasons why that works is because it doesn't say this thing has to work for everything in the ring. It just says it has to work for everything in the subring. That's why it can change. You shrunk down to a smaller set. Anyway, sorry. I just wanted to mention that as far as rings go. All right, so anyway, we talked about integral domain. Field then means everything has a multiplicative inverse. All right. So it's an integral domain in which every non-zero element has a multiplicative inverse. This is the easy way to think about it. Fields have to be commutative. If everything has a multiplicative inverse besides 0 and it's not commutative, that's what we call the division ring. I'm not going to do much with division rings at all. I think I told you to look at that one practice problem that had to do with the quaternions. That's an example of a division ring. Pardon me. In particular, if it's a division ring, it has to be infinite. There's a big theorem. I believe it's the Vetterberg-Artin theorem, if I remember right, but it says that a finite division ring has to be a field, which is interesting. If everything in a finite ring has a multiplicative inverse, then the multiplication actually had to commute. That's a big structure idea. Those, to me, are the most interesting theorems in algebra, because it's actually talking about what the structure has to be. So, in any event. The important thing is that you know what a field means. So that if I ask you, is this a field, you can tell me why or why not. The big thing that you're looking for with field is commutative, and everything has a multiplicative inverse. That's that's really what I care about for fields right now is, do you know what the definition means? Do you know what the words mean?
It's a large plane of grass. Any other answers?
It's an area of study. Oh, it could be magnetic. It could be.
Everything except our wrong answer.
Rings are those things you wear on your fingers.
Yeah. It goes around a rosy. All right. Oh goodness. Like I said, with the different properties that we have, and making sure that you know the different axioms, in particular, making sure you know how to do the distributivity idea for, like I said, filling out the multiplication table like that. Again, not going to be 8 elements. That's a lot of multiplications to do, especially when it's not commutative. However, again, you should be able to gather really quickly what the multiplicative identity is there. I did give you that one there. It's E. One of the reasons why I used E is because that's a pretty typical instead of using a 1, that's pretty typical for using the identity in a group, is an E. So we'll see that. For rings, we usually use 1 for the identity, and then in groups, we use E for the identity typically. So that was why I used E there. One of the reasons why we use E is because the first letter in the German word for identity is E. It's Einheit. A lot of algebra has roots in German. A lot of the original papers are written in German, so that's why we use a lot of letters that don't make sense for their abbreviations, but it makes sense if you know German. That's why we use Z for the integers. It comes from Zahlen. Yeah, I don't know a lot of German. I just know that I know a little bit. Anyway, that is pretty much everything, I think. This test is going to be a lot. I mean, there'll be some short proofs on there, but it's more about, do you know what the words mean to be able to provide examples or provide counterexamples on the flip side. Like I said, the big things about doing the proofs that we're going to be doing. Can you prove something is a subring? That should be something you should be able to do. And then being able to do some proofs with divisibility or something that might involve a division algorithm. The big thing, like I mentioned before, the big thing we used with division algorithm was writing an integer as maybe 4k plus 4k plus 1, 4k plus 2, 4k plus 3, right? Those are the exhaustive possibilities if you divide by 4. Example like that, right? Knowing that your GCD can be a linear combination, we've used that several times, right? So being able to do that. The proof should not be long and involved. They should be, do you know what the words mean? Do you know how to rewrite them based on what the words mean? Those kind of things. Shouldn't be horribly tricky as far as that goes. And then again, like I said, do you know what the words mean? Those pop up in true-false questions, or the concepts also pop up in true-false questions, making sure you know what things say and what they don't say, right?
Yeah. This question is going to be a little more basic because I'm totally blanking looking at this chart right now.
Mm-hmm.
When you read the multiplication chart, is it top then side or side then top?
Side then top.
Okay.
Yeah. Good news is if it's commutative, it doesn't matter.
Just how I got away with.
No, so this would say that B times C is B, for example.
Okay.
Yeah. A times F is 0. It's always, yeah, we do it left and then top. What's interesting is, I mean, that's the convention for both rings and groups when we get to groups. But sometimes your operation is function composition. So even though you mean left, right for the operation, function composition means you work inside out. It really looks like you're doing right, left. So just to make it more confusing later on. That's what you want to hear, isn't it?
Yeah, love to hear it.
Mm-hmm.
Love it.
Love it?
We'll survive.
It'll be fine. It's all good.
Everybody here is going to make it through this class. We got this.
That's the plan. Other questions at all? Feeling confident? No.
I wouldn't go
Everyone's like, no.
The confidence I have feels vaguely unfounded.
Like I said, if you know the definitions, know how to do examples, know how to find the different things that I ask you for. Like if I give you a multiplication table, you can tell me what the multiplicative identity is, or tell me there isn't one. Can you pick out units? Can you pick out zero divisors? I mean, if you can do those kinds of things, you're going to be able to do at least half the test at that point, right? So, knowing how to do is just the example parts and how to be able to read the tables and those kinds of things, it's going to get you a long way. The rest of it's going to be, do you know what the words mean? Maybe.
It's like learning a new language.
Yeah, it is. It is. It's fun stuff. Because I think it's fun stuff.
You would, wouldn't you?
I would. Yes, I would. I would. I think it is pretty fun. Then I got to figure out what we're doing next. Because I'm not sure I'm going to do the next section in the book next. Because I don't think I want to do it yet. But then I got to see how it affects farther on. So, like I said, I got till next Tuesday to figure that out. Well, I've not used this book before, and like I've mentioned before, I've not taught it in this order before. And then I come across things and I'm like, I don't think I'm ready to do that yet, because that's not the way I want to think about it. The issue, well, the issue is when you get a lot of classes taught by the same person, you get how they think about that particular area. So, for example, when was that your stomach?
Yeah. I did not eat breakfast.
Oh, I'm guessing you're hungry then.
I'm
Yeah,
very hungry.
I bet. Was it?
Leaning forward, because if I lean back, I'll join the symphony.
That's awesome. But one of the issues is when you have a lot of classes taught by the same person, you get how they think about things. So a lot of things you get from me is I think about it as an algebraist from that perspective. So it's good to see other people's perspectives on different topics. Because if you see me all the time, then I mean it's good to see my thoughts on algebra as an algebraist, but when you have me teach other things like numerical analysis, you get numerical analysis from an algebraist, which may or may not work.
I don't know. I still have all my files.
Yeah. Oh, cool. Well, good. But generally speaking, it's good to hear different perspectives by different people in different areas because you get different ways they think about things because not everybody thinks about things the same way.
Now that you mentioned that I am the only one in here who's also in that Calc 3 class,
Mhm.
I realized that all of those comments were pointed at me. And that I nodded along to things I really shouldn't have nodded along. It's like, yeah, somebody in here gets this.
Maybe.
Uh-oh.
Uh-oh. That's hilarious.
She was complaining earlier about how she doesn't know which parts